Alright guys, we're gonna do number 51 here. A test rocket is fired vertically upward from a well at a catapult. It gives it an initial speed of 80 meters per second. So you have a rocket. Let me draw the rocket here. And this rocket is going to be fired from the well, whatever that well is. Okay, there we go. Beautiful rocket. And this rocket has an initial speed or velocity, if you're talking at b naught being, and I'm going to use the variables here, 80 meters per second. It engine accelerates at 4 meters per second square. Let me so, and then here you can have an acceleration of 4 meters per second square. I'm just putting the variables just to get started. An engine then fires and accelerates at that until it reaches an altitude of 1 kilometer at 1,000 meters. At that point, its engine fails and the rocket goes into free fall with an acceleration at 9 meters per second. For what time interval is the rocket above the ground? For what is the maximum altitude and what is the velocity just before it collides the Earth? You will need to consider. I don't need to consider anything. All you need to know is know your mathematics, folks, and you're good to go. So here you have a rocket that fires, and it's going to accelerate upward. So it's and it's going to reach 1,000 meters. Once it reaches 1,000 meters, engine fails. It's going to just free fall towards the ground. So there's a two-part motion to this problem. I encourage you to go to the pause this video to get the problem solved. Presuming you pause this video and give this problem. Before I do, let me set up the motion problem. Let me graph this a bit. So this is going to be the t-axis, and this is going to be the y-axis, not the axis, the y-axis. And it has an initial velocity, so it's going to start going upward until it reaches at a height of 1,000 meters. So that's going to be the height h. And then an engine, so at some specific t naught, which I'm going to call it, I guess I'll call it t1, I guess. I was going to call it t naught, but I'm going to call it t1. And then an engine fails. So from that equation, we can already set up that y, and before we do that, let me set this other one up. And then it's going to reach, and then it's going to keep traveling upward until it reaches its maximum altitude, and then it's going to fall back towards the ground. So that's the motion, folks. And the motion is going to be y equals some initial velocity times the t plus at squared over 2 from the time interval from starting from t to t1. So after t1, you're going to have some final velocity being some initial plus at, and I'm writing it this way. So and that final is just going to be, I'm going to call that t1 here. So now you're going to have another motion being y equals some initial height plus some final velocity. The velocity at this point, that little slope right there, times t after t1 minus g over 2, and remember that g is the acceleration of gravity, which is 9.8 meters per second square. t2 minus t1. In fact, I'm not going to call it t2. I'm just going to call it t. That's my traditional way I like to define my variables. Anyways, so this is the motion, folks. And notice that I don't have any of this memorized, even though I do now because I actually solved this before. So notice that right here, folks, I'm going to call that T2 when it hits the ground. So notice, folks, that this is going to be the motion graph right here, already set up for you guys. So the question is asking for what time interval is the rocket above the ground. Well, before we do that, let's find out what V1 is. And V1 here, I define it to be some initial velocity added to the acceleration times the time, specifically being t1 at the point where the engine fails. So in order to do that, we need the variable t1 here. But we can get that. We're going to use that equation being, let the final height be 0 at that point. At v1, let this be t1 plus a t1 square over 2. And notice right here, folks, that t1 is a solvable variable. So we're going to minus the h on both sides. Let that be 0. So v naught t1 a t1 square over 2 plus this. I'm just writing it this way because I'm going to use the quadratic formula. So this is the only variable unknown here is going to be t1. And t1, we can already solve this as being negative v naught plus or minus the square root of v naught squared. This is a quadratic formula, guys, in case you kind of forgot that. Minus, or with minus to switch to a plus, simplify the thing. This will result in 2ha all over 2a, or in this case just a. And since and this parabola and this motion, this is going to one of the values is going to give us a negative. We're going to exclude this value because we only care about the positive portion. So all we have to do is put this in the TI-84 calculator, use your tools of mathematics if you have any, and solve them. So once you solve for these variables, folks, you're going to say that t1 here is specifically 10 seconds. So at 10 seconds, that's when it reaches 1,000 kilometers, even though my graph sucks. And that's when the engine fails. So once we have that, let's find what V1 is. V1 is going to be 80 meters per second added to 4 meters per second square times 10 seconds. From there, V1 is just going to be 80 plus 40, which is going to be 120 meters per second. So we already have two variables. So that's all. So once you're given the time it takes at this point to reach a height of 1 kilometer, then you can get the final velocity being the new initial velocity being 120 meters. And we're going to need that just to make it easier because I don't want to, so to get this other equation, y being h plus the final velocity being v1, t minus t1, and remember, folks, that this is 10 seconds, so t1 is already solved, minus g over 2 t minus t1 square. So from here, once you have the final, the only unknown here is t. What you guys could do is you could, FOIL this and simplify and turn this into a quadratic formula, which looks like a mess, or you could straight up do the quadratic formula. So I'm going to define this to be at t2, specifically when the height here, when the position here is 0 meters. So actually, let's put this on the side here just to make it nicer here. So notice, folks, that this is actually pretty straightforward once you understand this, folks. Like you'll realize that, oh my God, this is actually not too bad. Yeah, and it's not. And I don't know how the back of the book solves it, to be honest. And to be quite frank, I don't really care. So I'm just solving it the way I know, I figured it out, and the way I know. So I'm going to do the same thing. I'm going to do the quadratic formula. Negative v plus or minus v1 square minus 2. And notice that this is going to be a minus and a plus. So I'm going to switch this into a plus, 2gh all over negative g, because that 2 over 2 will cancel off. Now, before we do this, folks, let's think about this. This formula is this parabola right here. Okay? So notice that there's a negative. And notice that this is a negative in either a plus or a minus. Or either this could be a plus and that's a minus. Or wait, if that's a plus, yeah, then that's a minus. So, but I'm going to just simplify this and distribute that negative sign and just change that into a plus, just to make it easier for this. And from already, you can already you can plug in the variables. And once you do that, you would have this equation resulting in 31.06 seconds. seconds. And then we're going to add the T1 on both sides. And once you do that, once you add the T1 here, T1 being 10 seconds, the time interval where the rocket is in motion above the ground, which I call it T2, is going to be 41.06 seconds. And I already solved for part A right there, folks. That was beautifully well done. Now let's solve for part B. For part B, for what time interval, which I'm going to call T max, to get this specific Y max. For what time interval is the what is the maximum altitude? In order to get the maximum altitude, folks, notice that this is going to be the other equation that I've already set up for you. So I'm going to take account to this equation, T minus T1 minus G over 2T minus T1 square. I'm going to take the derivative of this to respect to time. So now you have dy dt, that's the velocity of this graph to respect to time. So that's going to be that velocity. Is going to be this. This is going to be 0. That's just going to be v1 minus the standard g of the t minus t1. And that's just going to be all we're going to need. So notice that that little trick, folks, is just taking the derivative. And we're going to let the velocity of that particular motion be 0. So once you have that, then you can just simplify, use your rules of algebra, plus gt1 equals 0. And gotta not get sloppy here. So there we go. I did wrote down the final answer regardless. So the time it takes for it to reach yeah, I'm getting a little sloppy. Okay, this is T1 and this is T max. So okay, so T max is going to be V1. I'm going to move that and then at the GT1 divided by G. There we go. Beautiful. Okay. So V1 being 120 meters. So we're just going to plot G. That's 10 seconds, by the way. T1 is 10. And that's going to be divided by G. And I think that's exactly what I had. So that's the time it takes for the Tmax. So Tmax here is going to be 22.24 seconds. We're going to take this time. We're going to plug it into this original equation, y as opposed to 22.24 seconds, to get the final result. So when t is 22.24 seconds, the y max is going to be specifically 1734.69 meters. So that's 1.7 kilometers right there, as I would put it. So that's it, folks. Then let's see what part C is asking. For what is its velocity just before it collides to the Earth? Oh, that's pretty straightforward. Okay. We do know the time, which is 41 seconds. I think that was T2, right? Yeah, so T2 is going to be 41.06 seconds. So all we have to do is take the initial velocity, 120 meters per second, minus 9.8 times 41.06 seconds. And that's going to be the final velocity. So we're just going to do that. I'm going to store this into my TI-84. I like to do the exact values. You guys can maybe approximate it with 2 decimal places. What the fuck? Oh wait, I got 522, but I what the 282? That's not what I got. Oh, I'm an idiot. 31.06 seconds. Okay. I was like, what the fuck? That's not what I got. No, but oh, I was so close. Okay. So 120 meters minus 9.8 times this interval. Okay, yeah. So that makes sense. It's actually t minus that t1. So anyways, once you do the math correctly, the final velocity is going to be 184.39 meters per second. So that's the velocity as it hits the ground. And to be quite frank, that's a really high-ass speed right there to be hitting the ground at that. That's going to literally blow up the rocket or something. That's going to mess it up. But anyways, folks, and the hint is actually pretty good. I usually don't need the hint though, but do follow the hint. You will need to consider the motion while the engine is operating separate from the free fall motion. That's what this is, folks. This is a separate motion equation. So one of them, this is the motion from the interval from 0 to t1, and this is the motion from t1 to t2, folks. Think about that when you set these problems up. Don't just blindly plug and chug, but actually know what the fuck you're doing. So we want intelligent engineers, folks. We don't want some dumbasses running this country anymore. We want scientists. Anyways, folks, I hope this helps. Let me know in the comment below, and subscribe to the channel if you're new, and help this channel.